Good morning, everybody, and greetings to Argentina. My name is Franz Meyer. I'm an associate professor at the University of Alaska Fairbanks, and I'm also the chief scientist of the Alaska Satellite Facility, which is NASA's main data center for SAR data. Over the last few years, I've been specializing on the development of value-added products that can be automatically generated and are specifically targeting the disaster response community. So we've been building some tools that I want to present to you today that hopefully help you a little bit with accessing this resource SAR data sets and use it very effectively in your work, and especially in the disaster management work. And so as part of this presentation today, I want to start out with giving you an overview of some things initially that you've already heard today. So you've already heard lectures about what SAR is in general, how SAR processing is done, and what interferometric SAR is. But I want to summarize those a little bit in the beginning, specifically for the from the viewpoint of hazard monitoring. Once that's done, in the second part of the presentation, I want to talk about some strides the community has made in order to make these data sets more useful to you. I want to talk to you about available data sets that have improved over the years. I also want to talk to you about how you can access these data sets easily. And then in the main part of the presentation, present to you some value-added product services that were developed over the last few years and provide you with already processed data sets that you can directly integrate in your work, hopefully, at least. And we'd love some feedback on the quality of these products from you. And then at the very end, I'm going to give you a short summary and also some information on further readings. So for all of you that have been working in hazard management for a while, you know that especially when you live in places like Alaska or Argentina, which are vast and not very heavily populated, there's really no way around remote sensing if you want to do large-scale hazard monitoring or environmental management. So SAR data sets have been used for a variety of things, from the observation of volcanoes and glaciers and earthquakes to the management and monitoring of flood events or events like oil spills. So it's a fairly flexible tool. But if you want to really utilize SAR data sets or any remote sensing data sets routinely in hazard monitoring, these data sets have to meet certain criteria. You want the data sets to be of high resolution and large coverage so that you can see the details that you're interested in over the scale that you need for observation. You want them to be frequently and reliably observed. So you want to be able to count on when the next acquisition happens. So that's really a very important component of a hazard management or monitoring system. You want, ideally, because, of course, hazards happen everywhere, you want the sensor to have a global observation strategy. And in the end, you want to be able to utilize very long time series. Because you might want to compare, the state of the environment now to the state of the environment 10 years ago to assess changes in hazard likelihoods or hazard likelihoods in a certain area. And so the optical community has lived for us how to really do this effectively. So what you see here in this little animation is an analysis of an area around Las Vegas using Landsat datasets. So 30 years worth of Landsat datasets, as you can see, have this capability. We have in this area reliable observations, and we can use that to understand the development of the urban environments in Las Vegas, but also sort of changes in Lake Mead that happen over the long time span. So this is really the kind of data set we want. However, while this works with optical data sets really well for dry places like Las Vegas, what you see on this map is that for large parts of the globe, cloud coverage is really preventing you from doing very effective optical remote sensing. So you have all these white bands that you're seeing in this data set. Those are areas where cloud cover really prevents optical data sets regularly from seeing the ground. This really has, the problem with that is that your reliability of your data set is going down. SAR can help you here because SAR has the ability to penetrate through clouds and observe the ground 24/7, as you already know at this point in time. And so this is an example of how this can be useful for you. So you see here the observation of a volcano in Alaska. This is Mount Cleveland in Alaska, which was active in 2011. And actually since 2011 again. What you see here on top is you see a dome growth in the caldera that you can very nicely see in these repeated SAR observations. And really only SAR was for this event useful because all the optical data sets in this area were cloud covered and weren't very useful for Earth observation. So SAR provides you this reliability. You can analyze repeated images, just the amplitude of these repeated images to understand the ground. But you can also do what you've already learned today in SAR processing. So you use phase differences between images, like shown here in this colored interferogram, in order to understand surface deformation. So all these fringes here are related to surface deformation. And those typically relate to hazardous events, something like volcanoes, where volcano deformation, as shown here, converts directly to phase measurements in an interferogram. And these directly relate to a hazard potential for this volcano. It's not the only thing useful for volcano monitoring, but it's a very useful data set for understanding volcanic behavior. Similar things can be said for other events. You see on this side over here, on the right-hand side, the Chile earthquake from a few years ago, and all these fringes relating to surface deformation relating to this earthquake. And there's some other examples of other earthquakes in Japan and also volcanic eruptions that we've processed. So it's a very useful data set for hazard monitoring, and SAR as a whole, both amplitude and phase, are quite useful. So however, not always was it easy to exploit these capabilities of SAR for hazard monitoring. And so only over the last few years we have made some improvements to systems and technology that allow you now to really utilize these capabilities. And I want to show two things. First, I want to talk about available data sets and the data set availability that has improved dramatically over the last few years. And then later on, I want to talk about services. So in general, SAR has been around for a very long time. We've had legacy data sets dating back all the way to the 1970s, late 1970s, when NASA at the time launched CSAT, which was in orbit and alive for about 3 months. Really repeated and more organized observations with SAR we have since the 1990s. So with the launch of ERIS-1 in 1991 and the continuous time series since then, we've had quite good coverage of the ground using SAR systems. This is continued right now. So these are nowadays SAR satellites. So you see things like TandemX, which is an X-band satellite launched by the German Aerospace Center. We have C-band satellites from RADARSAT-2 from the Canadian Aerospace Center. Cosmos Skymet in X-band launched by Italy. ALOS Pulsar L-band system launched by the Japanese Aerospace Agency, and then Sentinel-1, one of the flagships nowadays, launched by ESA. So we're continuing this wealth of data set that is available since the 1990s. And it's going to be even better in the future. We have more systems coming up. SAOCOM, of course, is the Argentinian representative here, system that's going to be launched in 2018, and you've heard of SAOCOM already earlier today. And then you have PASSAR, that's a Spanish system that's going to be launched. RADARSAT Constellation Mission, which is a set of satellites that are observing the planet fairly regularly. Then one system that I want to talk about, NISAR, which is an American launched space system, and then Biomass again from ESA. So on the first glance, if you look at this chart, you see density of SAR images throughout the past and now. But there are important changes that have happened since the past. And one of them is what you see here in yellow, or with a yellow border. All of these data sets shown in yellow here, those are freely available. So this is you see an important move here. All the future systems, at least for the South American country, all of these future systems here should be freely available to you for your research. Additionally, and you see in the past, data sets have not always been freely available. So that's an improvement that we've gained recently. Furthermore, you see these systems that are shown in red. These systems in red, like again, SAOCOM, RADARSAT Constellation, but also Sentinel up here, they are not only freely available, but also they also have some plan of regularly observing the planet to provide global data sets, or at least for your area of interest in Argentina, regular observations that allow for an incorporation of these data sets into hazard monitoring systems. So really game-changing developments that happened recently. If you want to look at these systems a little bit differently, you can also group them by the wavelength they're using. You see here on top X-band systems. These are short wavelength systems that are more suitable for doing urban monitoring. The resolution is usually higher for these systems, which lends itself well for urban analysis. While P-band and L-band systems down here, so the NISAR and the SAOCOM type SARs, they are more useful for natural environments, agriculture monitoring, natural disaster monitoring, and so on. And so you see here by the timeline of when these systems are going to be launched. On the other side here, you see also their repeat cycle. And you see nowadays these systems are all really observing the planet regularly with repeat cycles in the few days range. Another thing I want to mention is these, you can group, if you want, these data sets a little bit by their spatial resolution. You have, on top here, I'm showing you the systems that have moderate 10-meter type resolution. Those include ALOS Pulsar, Sentinel-1, also the NISAR, SAOCOM, and these future systems. They are great for you for doing background monitoring, for looking at hazards of intermediate to large scales like subsidence in urban environments, earthquakes, deformation related to earthquakes, larger landslides. They can be monitored well using these kinds of systems. They're also good for just general background mapping, to provide yourself basically with a background map against which you can compare future acquisitions. The higher resolution class, these are the 1 meter type class data sets. Those include many of the X-band or shorter frequency missions, TerraSAR X, TandemX, PASS, Cosmos SkyMed. Those are then great once you did a survey with the intermediate resolution systems. You can use these higher resolution data sets to zoom in, look at smaller scale signatures like the deformation of building and bridges is shown on top, the measurement of sinkholes and smaller landslides. And because they usually have higher repetition frequency too, they're also better at looking at very dynamic signals. So they have all their different capabilities and advantages and disadvantages. Note, however, that many of these medium resolution systems on top, they are typically either free of charge or very low cost, while the higher resolution systems are more expensive. So, and also partly not as easy to get. So consider that too when you try to incorporate different sensors in your work. So going back to the sort of the game-changing developments that have happened over the last few years, let me highlight to you two important sensors. I'm not going to talk too much about SAOCOM in my presentation because you have the experts about SAOCOM in the room, and I'm sure you've heard all about SAOCOM over the last few years and the promise and the sort of the great promise it has for the South American continent over the next few years. So one thing that I want to point out, though, one candidate for operational monitoring that is already in space is Sentinel-1. So Sentinel-1 is an ESA-based really constellation of satellites. It's a combination of 2 satellites that together allow for regular observation of the planet. One thing that was game-changing about Sentinel-1, or is game-changing about Sentinel-1, is that it's the first SAR with an operational mission. What this means is that it was built and is meant for operational monitoring of the planet. And this comes with a requirement to observe the planet reliably and regularly in hazard zones, which are large zones of the South American continent. Also, there's a requirement for observing with every pass, which is every 6 days. For most of the planet nowadays, we get data sets every 12 days reliably. The other requirement was that it has to regularly image all land masses, many coastal zones, and many shipping routes. So this requirement didn't exist for other SAR missions before. And finally, it's interesting because it was built for INSAR, so it can do the full suite of hazard capabilities that I talked to you about before. It can do image, you can get images from it, time series of images for change detection, and you can use INSAR for looking at deformation. And of course, very important about Sentinel-1 and a total game changer in SAR also is that all data sets from Sentinel-1 are free and open. So they're very easy to access and they're completely free free to use for your work. If you wanted to look at the global distribution of data sets, this is a map. This is not the most up-to-date map. This is from August last year. But what I want to show you are the different colors. You see in yellow the hazard zones. These are very frequently covered every 6 days nowadays. There's, of course, a lot of coverage in Europe, which makes sense given that it's a European mission. But if you look at Argentina, you see that most of the planet has really good coverage with Sentinel-1 data with a high repetition frequency of nowadays 12 days. And this is tremendously useful, even if you only do image analysis. When you look at this animation here, this animation shows the export of sea ice from the Arctic through the strait along Greenland. You see sort of how ice is coming down the strait. And, not much processing is done here. Everyone can understand what's happening here. It's very easy to analyze. Once you have these dense time series, you really can dig in and analyze these dynamic processes on the planet. A future system that, in addition to SAOCOM, is going to be very useful for you for this work is NISAR. NISAR is the future American SAR mission. NISAR stands for NASA ISRO SAR, and therefore it's a collaboration between between NASA and the Indian Space Agency in this case. Similar to Sentinel-1, it was built for INSAR. It has the promise of providing reliably repeated observations of all the land masses. It is therefore very useful for hazard monitoring processing systems that sort of rely on this routine incoming data sets. Also NISAR is going to be fully free and open. As I said earlier, it's planned for launch in 2021. It's in L-band, so it's very similar to SAOCOM in its properties and will sort of continue the heritage of SAOCOM into the future. So if you start building or absorbing SAOCOM starting next year, you can use the same kinds of processes also if you want to integrate NISAR in your work. One thing that's interesting about NISAR and different to most other SAR missions is that it's a fully two-frequency SAR. So it has the capability to operate both in L-band and in S-band, which is sort of at sort of half the wavelength, is somewhere between what SAOCOM does and what Sentinel-1 does provide to you right now. So that's a unique capability. It is not there's no promise that L and S-band data will be available everywhere and all the time, but there will be data sets for you to analyze and sort of analyze what you can gain from two frequency observations. The system has a wide swath, so we talked about high resolution wide swath capabilities. NISAR provides swaths of up to 240 kilometers, as you see here, and at the resolution in the 10-meter range. So it's a decent resolution and a very, very large coverage. So it's going to be very useful for your work. So all of these changes have happened, and so now SAR is really, with Sentinel-1 and these future missions coming up, it's really ready for use in more operational systems. And of course, for that, you need to know how to get to these data sets. How do you actually download them? You will get a PDF version of all of these slides, I hope, delivered to you during these days of this workshop. And what I show you here is just a screenshot of the so-called Vertex System. This is one of the two large search engines that you can use for downloading Sentinel-1 data. And also in the future, you can use the same system for downloading NISAR data sets. If you have the PDF in the end, you can click on this screenshot and it will directly lead you to the interface. It's a very easy to use graphical user interface where you draw bounding boxes on a map and you can download data easily. There is a login required when you come to this webpage for the first time. It's a very simple login. All that's required is a name and an email address, mostly to prevent automatic download bots from hijacking the archive, basically. But once you have signed up, which is free and simple, then all these data sets that are in the archive are yours and for you to use. So you can use this interface. You can also use the interface provided by the European Space Agency. That's the so-called ESA Science Hub. Again, this is the screenshot for the Science Hub. And similarly here, a login is required, but it's very simple. It's the same kind of information that is requested by ASF. And then once you're in there, simple drawing of bounding boxes allows you to find and download all of the Sentinel-1 datasets held and acquired by ESA. So please give this a try. Should you have any issues with accessing any one of those to archives, please send me an email. The very last slide, I have my email address, and I can get you hooked up so that you can get access to these datasets. So moving on from datasets, another important thing that I want to cover today is value-added services. And so you may ask, why do we need value-added services? Why do we need systems that do some of the processing for us? Well, our experience is that a lot of the new users that are coming online now, that datasets have become free and open, they have some difficulties with understanding these complex SAR processing algorithms. So typically, the processing flows that are used to create information out of SAR datasets are not always straightforward. And there are a few reasons for this. One of them is that the data formats in which SAR datasets are delivered are often not so easy to understand or easy to read, and they're also different for different sensors. The other thing is that SAR data often are not geocoded. If you download optical datasets, many times they come already in a geographic coordinate system. SAR datasets typically do not. And also because images are side-looking, so SAR images are acquired in a side-looking geometry, they usually are very distorted. So geocoding is a mandatory step and not always straightforward to do. So we take geocoding away from you and make it a little bit easier for you to ingest datasets. Also, SAR, as you may have heard earlier today, I guess, it has a lot of noise features in them. So if you want to do change detection with them, also that is not always straightforward to deal with. So we try to take that difficulty away from you and make it a little bit easier. And also INSA processing is error prone. So we try to take all the complexity out of it, do all the processing locally and deliver you a product. Other reasons why it makes sense for you to try to utilize these services is that SAR processing is actually very data intensive. So you incur very large data volumes when you do SAR processing, and it's just easier for you if you can outsource that to a data center like us. And finally, SAR processing, if you want to install your own SAR processing tools, it turns out these tools are really still at a stage where they're not super user-friendly. So that's another reason why you should, we try to take some of that heavy lifting away from you. And hence, community, not just us at UAF, and there are other people that have invested quite a bit of time in developing these value-added product systems. I'll show you 4 of those today. So this is why we need those and why those are usually being designed. But the question is also, what do these systems usually provide to you? What's the type of data sets that you can get? And there are really 3 types. The first one seems trivial. The first one basically is a geocoded product. So what these systems are doing is they're geocoding and fully terrain correcting images for you, so that you can just grab the result. It comes in a GeoTIFF format, and you can plop it into your GIS system and can analyze it. And so just as an example, this is a data set that was not topographically corrected. So you may see some distortions in some of the topographically inclined areas. You'll see that definitely when I show you the corrected image. So what we usually do is we correct for the geometric distortions, which you see here. So if you go back and forth, you see how the geometry of the image is changing because we're correcting for the geometric distortions. The other thing we do is we typically take the shading of the image away. You see, if you look at the mountains, how one side of the mountain is brighter and the other side is darker. And we try to correct for that as well. Even though it makes the image look nice, it often is distracting when you try to do change detection or when you try to just physically analyze the image. So we usually take that component away from you also, and then image, you may say, looks a little more boring, but in fact it is actually much easier to deal with if you do multi-temporal image analysis or just single image physical analysis of a data set. So this is done automatically by most of these systems. If you want to learn what's happening within when geocoding is being performed, there is actually information available for you online that you can utilize, and you can learn yourself how to do geocoding and terrain correction of SAR data. So one resource is linked here. So if you click on this link once you have the data set, or if you only get the video, and you can just type in this link if you have to. It leads you to a web page like this. So the web page that you see over here, which is an online resource of SAR information. It has a lot of lectures on SAR, but it also has a lot of labs. This is particularly a lab that geocodes SAR data sets and walks you through the processing steps of geocoding. So there is some ability for you to learn how to deal with these data sets yourself. A second kind of product that is produced by these processing tools usually are change detection maps. And I show you this really in an example. I showed you in the beginning, when I showed you this time series of a volcano, SAR has very good ability to detect changes between images. And so we utilize this, for instance, for doing flood mapping using automated tools. So this is an example of a flood that happened actually in Alaska, so it's not super relevant for your area. I apologize. But still it's a flooding event on the north slope of Alaska, which happened a couple of years ago. What the system internally does is it takes repeated SAR images. So what you see here next to each other is an image acquired in 2015 all the way over here on April 13th, and the second one acquired on April 15th. And so there was flooding happening between these two data sets. We performed first an initial approach where we try to suppress all of the background information in these images and emphasize the change. So you see here these features that you see in the image now, these are all the areas where actual change has happened. And then we use a sophisticated masking algorithm to create these change masks for you. So these are automatic algorithms that are implemented for you to use. Again, if you are really interested in learning how to do change detection and what the specific advantages and limitations of SAR-based change detections are, again, want to refer you to some online material. This is the link here again leads you to an online lab. This is the screenshot of this lab where I tried to walk you through the process of change detection using available data sets. Actually, in the lab, the change detection is done simply in a QGIS or ArcGIS environment. So if you have ArcGIS available to you, you should be able to follow this lab along if you want to learn again how to do change detection yourself. Finally, a last type of data sets that is typically produced are interferograms. And so, as you heard earlier today, interferograms essentially, interferometry takes two images acquired at different times. So this is the amplitude and the phase information, and uses those to calculate interferograms. Initially, you can use a single pair to get one single interferogram. If you have sort of a time series of data sets, you can create a whole time series of these interferograms if you want to follow a deformation event along. Typically, we need a DEM in order to subtract topography influences on the interferometric phase, but then in the end, we end up with these deformation fringes that relate to hazard events. So this is, again, this event that happened in Chile a couple of years ago. So please, also here, online resources exist that tell you how to process these data sets. Follow this link. And again, there are examples of how to process in SAR data with publicly available SAR tools that you can easily install and download. So these are the types of data sets. In the following, I want to show you 4 systems that provide value-added products already for you. Let me go back. This first system is called SAR views. SAR views is actually the technology that's in the operational system, and the interface that we're using for running the system is called HYPE, and I'm going to explain that to you. SAR views is some work that was initially funded by NASA Applied Sciences. What the goal in general of SAR views is to take SAR datasets coming from Sentinel-1 and process them all the way through to a set of hazard products. And then take these hazard products and channel them. The idea was to channel them into operational systems. In this case, initially the plan was volcano monitoring systems. So we channeled them into the Alaska Volcano Observatory's monitoring systems for use. But within SAR views, we've produced automatic workflows for in-cell processing, as I said before, ending up in these interferograms up here. But we also produced workflows for amplitude analysis, which produce both just geocoded image time series, which you see here, but also these change detection maps that I talked about earlier. So those are all automatically implemented. Data sets are initially provided as HDF5 files and archived. And actually nowadays we archive everything in the cloud in cloud-based systems. But they will be delivered in the end. They are delivered as GeoTIFFs. So when you access these data sets, you can access them in a GeoTIFF format. Initially, as I said, this was a project that was meant for volcano monitoring, but because these capabilities that we developed are useful for all kinds of hazards, we expanded our services quite a bit. As part of this, we needed to migrate to a processing system that is provides you a lot of flexibility and can respond to demand by scaling up automatically. So we worked with the Alaska Satellite Facility, and we fused our processing capabilities with the ASF's so-called HYPE system here. HYPE is a cloud-based data processing pipeline, and we fed all of our algorithms into that processing pipeline. Why do you care? You care for two reasons. First of all, HYPE has a graphical user interface that you can access. So if you follow this link up here, https:// and then HYPE hyp3.alaska.edu, it leads you to the HYPE interface, and you can actually go into HYPE and run your own value-added processing production systems. You can define an area of interest on the map, and you can say, I want to have geocoded data sets for this area of interest from now on until next year, for instance. So it allows you to come in and utilize all these features. But for us, the big advantage was that we can now utilize all of the cloud-based processing capabilities like elastic scaling, so we can process large data volumes in really short time, and we can deliver data sets to you really effectively and quickly. Stay tuned for our hazard portal that we're currently developing. So all the products that are produced within SAR views, they relate to large hazards, mostly volcanic eruptions and earthquakes. And all the SAR-derived data sets we are throwing up on a webpage. The webpage is developed. We haven't really fully gone live with it. We are working out some last kinks, but this is sort of what the webpage looks like. So you have a map with like symbols where all of the hazard events happened. You click on a symbol, you get to a subpage, and you can download all the relevant and respective data sets. So please, if you want to utilize the capabilities we developed yourself, I encourage you to follow this link on the screen and start creating your own subscription, process your own data sets, ingest them into your workflows, and see how useful they are for you. There's a feedback button somewhere on the screen, so if on the web page. So if you have problems, if you have suggestions, you can either email me or you can just email feedback directly to the team. Oops. A similar service has been developed by JPL, by the Jet Propulsion Lab, one of the big NASA centers in the United States. This system is called ARIA. ARIA stands for Advanced Rapid Imaging and Analysis. It's a SAR-based analysis system that initially was particularly designed for the monitoring of volcanoes, of earthquakes, the automatic monitoring of earthquakes. But also since it has been expanded to all kinds of of hazards. Some of the advantages of ARIA compared to our own service is that it's a full multi-sensor approach. So it doesn't only rely on Sentinel-1, but it can also ingest other data sets. Otherwise, the collection of products is reasonably similar. So we can utilize all of these sensors that are shown on the screen. It all does, similarly to our approach, cloud-based processing to value-added products. The products are very similar, interferograms and change detection information, and they do that nowadays for a wide range of different applications. ARIA has supported also a whole list of different events. All of these are shown in this map here. So please, if you're interested in this particular one and you find it, please send ARIA a note and let them know how great of a job they're doing. This is an example of so-called damage proxy maps that are part of the ARIA system. These are similar to our change detection maps. They are providing information about where damage has happened related to a hazard event. None of these products, our product nor this product, are fail-safe, but they are a good initial indicator for where to look, where to send ground people, boots on the ground people to, and so on. Some of the products that are produced by ARIA are also publicly available. They can be found both on Earth Data Search on the NASA archive and on the ASF Vertex search engine. Here's some instructions of where to go and how to find these data sets. If you want to use ARIA yourself, ARIA also has a graphical user interface that users can use to create their own data sets. Please send an email to this email address, and JPL might be able to help you out with an account. A third one that I want to emphasize is a service called COMET. COMET is the Center for Observation and Modeling of Earthquakes, Volcanoes, and Tectonics. It's a British group that is directly linked to, that are sort of operating on behalf of ESA. So ESA got them a big grant to develop value-added product production chains. Also their approach is very similar. The idea is to produce value-added products, particularly INSAR products, to monitor geodynamic or geophysical events. They're focusing on the large hazard zones. Argentina is probably only partly in that, but sort of all the earthquake and volcanic regions in the world, that's the goal of monitoring those. The system that was developed is also not dissimilar from ARIA and SAR views. It basically starts out with an automatic INSAR processing chain up here, producing geocoded products and interferograms. But then their long-term vision is also on the bottom to create systems that can derive modeling results, sort of geophysical or source model results from the data sets automatically. That bottom is not fully realized, but that's sort of one of the long-term goals of this system. So not only to provide data, but also provide solutions for geophysical model inversions. The current state of the system is quite nice. On the top, you see an interface, and here's a link to the interface also. This is a database that you can access where all the interferometric products that they've produced so far are being stored. They're being delivered in the form of shapefiles you see here. You see currently they haven't produced much for South America, but sort of for the Asian continent they have made good progress. So this is growing, so keep checking in, and as soon as you find data sets that are relevant to you, please download them, inspect them, and provide the COMET team feedback, also provide us feedback. The community needs to know how to make these products more useful and more accessible to you. They also are developing specifically a volcano database where they want to regularly observe volcanoes and provide not only data but also model solutions for these volcanoes. This is still a little bit in infancy, but it's growing. So if you look at this blog page, you can see, and if you sort of click on that over the next few months, you will see how the service is growing with time. And the last thing I want to point your attention to in terms of value-added product production is the so-called ESA thematic exploitation platforms. So ESA, as part of its Sentinel effort, has also been producing platforms where users can come in and do their own data processing in these platforms. So they're providing means for doing or building little processing chains and at an ESA-based processing center. But in addition to that, the idea is that users will also donate back or leave their products on this server so that other users can come in and utilize already existing products for certain events. So it's a nice idea. So it's a sort of a collaborative data processing and archiving system that they've been developing. What's interesting about ESA's exploitation platforms is that they are themed by geophysical signal. So there are various exploitation platforms for different applications. There's a geohazards one over here, which might be relevant to you. There's also a hydrology one, which is all the way over here. So for different types of applications, there are different themed exploitation platforms that you should also check out. So if you, I think on the previous page, I'm providing you, hopefully a link. Oh, there's a link on this screen on the sort of the left-hand side. If you follow that link, you get to the homepage. You can click on the individual exploitation platforms. It's very easy to get an account there, and please experiment with them. And again, I hope that these services are right away useful to you. If that's not the case, we would love to hear what you like about these services, what you don't like about these services. Please provide us feedback, and we can try to make improve our services in the near future. So this is sort of all of the ones that I showed you so far. These are services that we provide, and they mostly provide you some basic value-added data products. They give you images, they give you maybe interferograms, and they give you some change detection information. If you're interested in very high-level products, earlier today I think you heard a presentation on INSAR time series analysis, or maybe PS, permanent scatter INSAR, or persistent scatter INSAR processing. If that's something that you're interested in, there are service providers out there that would love to work with you, also in your part. So they're distributed around the world, and they can work with you to create these products. So there are these service providers. Some of these service providers are listed on this slide. We should go on this side here. So they're listed by name. Of course, they're all not for free. They're commercial companies, but they are really great at getting you started, delivering to you, robust solutions that meets the requirements that you've set. So again, if you have one-off projects and you want to explore some of these higher level processing chains like PS INSAR, please think about contacting any one of those companies. Maybe get a quote to get sort of your feet wet and to get into the game and see how useful this kind of data set is for you. So in summary, what I wanted to show you today is that the community, the SAR community, has really progressed over the last few years. We now have a whole suite of new SAR sensors in space already and upcoming. They provide to you wealths of data sets that are free and open. And they provide to you data sets that are regularly sampled so that for the first time, SAR really can make a meaningful contribution in hazard monitoring. So that's sort of the first point. And there are some really interesting players coming up with Sentinel-1 is already in space, but I think NISAR and SAOCOM, especially for the South American sector, will be real game changes in SAR-based Earth observation in general, but SAR-based disaster management in particular. We've also, another thing I wanted to mention is we've seen with the advent of all of these free data sets and regularly sampled data sets, we have seen an explosion of the SAR user community. So this plot that you see here on the top right shows you this is only ASF, that's the Alaska Satellite Facilities user community, the people that come in every month and actually are downloading data, so the active users, we call them. And you see how in the past, the number of active users was sort of constant. We always had about the same amount of users. But But since the availability of free and open datasets and regularly observed datasets, starting with the opening of ALOS Pulsar here, we have seen a real explosion of the number of users that are coming in and want datasets from us. This is great, but it also has the problem that many of these users are not traditional SAR users. They do not know the complexities of all the processing routines. And therefore, we have really tried to do two things over the last few years. We have ramped up training activities like the ones that you're sitting in right now, which is, of course, not only focused on SAR, but has a significant SAR portion to it. And we've ramped up what I tried to tell you in this presentation, these on-demand value-added production engines that can take all the complex processing procedures that you might not care about and take them away from you and produce to you a product that is hopefully easier to ingest and easier to use by yourself and your colleagues. So, so I hope I could give you a little bit of a sense for these services. Please note again that these services are growing, and all of these providers that I mentioned to you today, we are eager for feedback. So we want you to use them. We want you to tell us, of course, we want you to tell us what you like about them, but we also want to hear the things that you think are not perfect yet, because we want to be able to tailor them and make them useful for the broad community. So please use them. Please keep feedback coming. Email us, contact us, and we'll be trying to respond to you as quickly as we can. If you find that intriguing, if you think SAR is something that you really want to invest more time in, at the very last slide, I want to show you some additional sets of information that you can tab into to learn more about SAR. So first, I've mentioned that a few times, but over the last few years, I've gone through a big effort to try to take all my material I have on SAR, entire semester worth of lectures and labs and exercises, and I've put them all online and made them all freely available. So all on this webpage that you see linked here at the University of Alaska Fairbanks, you can find a lot of information about SAR, and please come in, grab what you need, read through it. If you have questions, again, please email me, and we can try to answer those questions for you. So that's one resource that you can tap into. Another resource that you can tap into, and you may have heard of before, and there are actually representatives of this group with you this week. You should look into ARSET. ARSET is a NASA effort. ARSET stands for Applied Remote Sensing Education and Training. They are providing a large wealth of online materials for you, webinars, etc., and presentations. They have a variety of different contents, but they largely provide it to you both in English and Spanish, which hopefully will be useful for you. And particularly want to highlight one specific session that was uploaded not so long ago. It's a session that specifically focuses on synthetic aperture radar with a set of webinars that you can look at through the ARSET interface. All of these are, again, freely accessible to you, and please look at them. And again, if you have feedback, we would love to hear that feedback. And finally, another thing that I want to point your attention to is the European Space Agency, together with the German Aerospace Center, have teamed up, and they're going to do a large online lecture series on SAR coming up this fall. So this is going to be hopefully very interesting, and I encourage you to log into these lectures and listen to these lectures. So there's a link again here, eo/courses.org. This is an ESA-based webpage, and on the front page you will see information on this online course on radar that's going to come up, and encourage you to sign up, listen to the lectures. Again, tell us what you liked about them. Tell us the things that are missing, and we can fill in the missing gaps. So this summarizes sort of my talk. I again apologize that I couldn't be with you in person. If we have WebEx during the session, then I'd be glad to answer questions for you afterwards. If that's not available, please contact me at fjmeyer@alaska.edu. I'm going to try to get back to you as soon as I can. So thank you for your attention, and I hope you're enjoying your time at the workshop, and I hope to hear from you soon. Thanks a lot.